The renin angiotensin system is an important homeostatic mechanism involved in regulating blood salt levels, blood pressure, and blood volume. Principally, it acts to increase these three things. The heart, as you know, pumps blood to the entire body. One of the major sites involved in the renin angiotensin system is the kidney. Blood passes from the heart through the aorta, into the renal artery, and then into the glomeruli of the kidney. Blood will enter the glomerulus via the afferent arteriole, and it will leave via the efferent arteriole. The glomerulus is a clump of blood vessels that sits in the Bowman's capsule. Other structures we can see here include the proximal convoluted tubule, distal convoluted tubule, collecting duct, and loop of Henle. Fluid from the blood is forced out of the glomeruli into the kidney tubule. The rate at which this fluid is filtered is known as the glomerular filtration rate, or GFR. Lots of things are filtered into the kidneys from the blood, such as sodium ions, potassium ions, chloride ions, and more. Sometimes some of this stuff is reabsorbed back into the body, other times it's left in the filtered fluid to be excreted in the urine. The higher the GFR, the more stuff moving through the kidney. This is important to understand for later. Now over here in the afferent arteriole is a group of cells known as the Juxtaglomerular cells. They sit in the wall of the afferent arteriole and they make and release renin. Renin is important as it ultimately causes an increase in blood pressure, blood sodium concentration, and blood volume. How do the juxtaglomerular cells know when to release renin? Well, the cells themselves can detect blood pressure changes depending on how stretched the afferent arteriole is, thus acting as baroreceptors. If the arteriole isn't very stretched, it would suggest there's a low blood pressure and therefore a need for renin to increase blood pressure. So near the bit where the distal convoluted tubule comes into proximity of the afferent arteriole, there's a group of cells known as the Macula Densa cells, which sit in the distal convoluted tubule. They detect sodium levels in the filtrate. It's sort of like an officer counting how much sodium is coming through. If there isn't much sodium coming in, as would happen if blood pressure was low, it tells the juxtaglomerular cells to release renin. An easy way of thinking about it is to imagine a hose pipe attached to a tap. The tap is sort of like the heart, with the water coming out of it like cardiac output. The hose pipe itself is like the afferent arteriole, the water coming out the other end like the GFR, and the pressure within the hose pipe like the blood pressure. If you have someone who's dehydrated and therefore has a low blood volume, their cardiac output, or the water coming out of the tap, will be a bit lower, and so their blood pressure will be lower. That means there's less stretch on the hose pipe, or the afferent arteriole, and the water coming out the other end, or the GFR, is going to be lower. The baroreceptor activity of the juxtaglomerular cells picks up the lack of stretch and causes renin to be released to fix the low blood pressure. Since there's a lower GFR, there's less stuff going into the nephron, such as sodium and potassium. The macula densa senses the low sodium and also tells the juxtaglomerular cells to release renin. Now let's consider what would happen in someone who's fluid overloaded. There's a lot more water coming out of the tap now, so cardiac output, blood pressure, stretch, and GFR will all be higher. Again, the juxtaglomerular cells pick up the high stretch and won't release as much renin. Since GFR is high, the macula densa will pick up more sodium and won't drive the juxtaglomerular cells to produce as much renin. Okay, so what actually is the renin angiotensin system? Well, the kidney makes renin, which enters the bloodstream and meets angiotensinogen, which is in the blood but produced by the liver. Renin causes angiotensinogen to be converted into angiotensin I. Angiotensin I travels to the lungs where it is converted by an enzyme called ACE into angiotensin II. ACE stands for angiotensin converting enzyme. Angiotensin II is what brings about the actions that we see. Firstly, angiotensin II causes vasoconstriction in blood vessels by binding to AT type I receptors. This increases peripheral vascular resistance, thus increasing blood pressure. Angiotensin II also travels to the brain, where it activates thirst centers to make you thirsty and encourage you to drink, which increases fluid in the body, which will therefore increase blood pressure. Finally, it will also act to increase sodium retention by the kidneys. By retaining sodium, you automatically retain more water, which will raise the blood pressure as well. The body achieves this in two main ways. Firstly, it causes aldosterone secretion from the adrenals, and aldosterone increases renal sodium reabsorption. Additionally, it will directly increase the reabsorption of sodium from the renal tubules. To summarize, angiotensinogen is converted to angiotensin I, which is then converted to angiotensin II. Renin from the juxtaglomerular cells does the first step, and ACE from the lungs does the second step. Angiotensin II is the main effector. It causes aldosterone secretion from the adrenals, vasoconstriction, thirst, and sodium reabsorption, all of which act to ultimately raise blood pressure. Thank you for watching this Medic in a Minute video. For tons of free medical school revision resources, visit our website. For mnemonics, giveaways, and medical school tips, follow us on Instagram and Facebook.